Let's talk about three-dimensional free body diagrams and the equations of equilibrium associated with those situations. After this lecture, you should be able to identify support reactions in a 3D situation, draw the free body diagram, and apply the equations of equilibrium to that three-dimensional free body diagram. Of course, there are example problems and group solving problems to go through in the lecture slides, so make sure you grab those from the course page. They're not included here in this lecture, but they are present in the slides, so be sure to look through those. And of course, watch my example videos and so forth. There are many situations where there are other types of supports than the types we have mentioned so far, and often those supports are used in the context of a three-dimensional application. So you see on the left a ball and socket joint. That's obviously three-dimensional because the ball can move around kind of like your hip joint can. On the right-hand side, you see a couple of bearings supporting a shaft, and you can't see all of the machine here, but it is still a three-dimensional force problem. So there's many applications in these in the sphere of three-dimensional machinery and free body diagrams. Now, the bearings are interesting. A lot of times students struggle with their intuition, especially if they have experience with some of these things. So if you have experience with bearings, you might know that these are called pillow block bearings, the one on the right. And they actually, there's usually a set screw where you can screw the inner rotating ring onto the shaft and prevent motion of the bearing along the length of the shaft. Now, usually the purpose of those set screws is not so much to hold the shaft in place as it is just to kind of hold things together. It's a fairly light grip on the shaft. There are exceptions to that, but that's the common setup with set screws. When we model these in statics, we often neglect the thrust loads, the horizontal forces. There's a tremendous variety in the actual types of bearings internally. Some of those are not made to take a thrust load, in other words, a load along the length of the shaft, and some are. So there's some nuance in the bearing, but for the sake of analysis, we usually assume that there's no thrust load. We also assume there's no moment. Now, this is probably a more valid assumption if you've actually worked with pillow block bearings, because a pillow block bearing has a bearing insert that typically has a hemispherical feature such that the bearing itself can rotate inside of the bearing housing, inside of the block, so to speak. And that allows misalignment. So the shaft can run through the bearing and not necessarily be perfectly perpendicular to the body of the bearing's housing. And so they're called self-aligning, not so much because the bearings themselves are self-aligning, but because the interface between the packaged bearing and the housing is self-aligning. So it's a little more valid to say that we don't assume that these bearings provide any moment support or any moment reaction to the shaft. We'll see that a little bit later. There's a whole table you'll need to mark in your book. Other applications. Why is all of this important? Well, there are many situations that are important. For example, here's a rod holding up an overhang. Now, when you design this, you've got to decide where the grounding point A should be for that rod that supports the overhang. You've also got to decide where point B should end up. Should it be moved out along the length of the awning, or it looks like maybe it attaches to a structure there, that's sort of a T-shaped structure beneath the awning? Understanding how changing the orientation of that support rod will affect the load in that rod is critical for this application. Otherwise, the rod might break. So this is a three-dimensional example of a free body diagram situation. So understanding how the loading changes as you move things around, in particular the fixed point at A, is important because you don't want the thing to fall on somebody's head as they're trying to walk into the building. Here's an example of something that looks kind of like an engine hoist or a floor crane. More generally, it's being used to raise a barrel that apparently weighs 350 pounds. Okay, well, hopefully you realize that at some point you might be able to load this crane where the crane doesn't fail by the material failing, but it fails by tipping, right? It could be that the barrel's heavy enough that it will actually offset the weight of the crane and pivot about the line formed by AB. And so how do you determine the largest amount of weight that the crane can support without turning over or without tipping forward? It's a good question. That's really what this part of the chapter is all about. All right, so in your book, you need to find table 5-2 and mark it. Just as you marked 5-1 for two-dimensional support reactions, you need to mark table 5-2 for the three-dimensional. And I believe they're less than 10 pages apart. But make sure you find it, make sure you mark it, and refer to it as you are solving problems in the homework. So, for example, case 2, where you have basically a cam interface, something where there's a smooth surface support. The only type of reaction that can appear there is a force normal to the surface, in other words, perpendicular to the surface. We assume there's no friction, and that goes with that word smooth. That word smooth tips you off to the fact that they're saying there's no friction on that foot. So think of it as a foot sitting on ice. And obviously, if there's not something else to support this particular scenario, that body's at an angle, it's going to fall or slide or something. So there must be more to this machine, mechanism, structure, whatever it is, than is shown here. But the point is that that type of interface can't support a moment in any direction and can only support one force in the vertical direction. Case 4, for example, is a ball and socket. Now, a ball and socket can pivot around. It has no resistance, for all practical purposes, to moment in any direction. And so the only types of reactions that can occur at the ball and socket joint are force reactions in all three directions. Case 5 is a single journal bearing. We were talking about journal bearings a moment ago. And notice that this shows two moments being supported. However, frequently we will not include those two moments. Obviously, the bearing is designed to not have any moment about the axis of the shaft going through it. That's a given. That's the whole point of a bearing. But it, in theory, could apply a moment in the Z and the X direction as shown there. But often when we analyze these situations, we consider it bad practice to have a bearing like this support a large moment load where the shaft is pivoting rather than just rotating. Now, also, even though there are, as I said, set screws to constrain the inner race of the bearing to the shaft, we don't assume that there's any significant force capacity of that interface and of the bearing. Now, obviously, things would be a bit different if it's a bearing that is designed to accept thrust loads. Some are. Most of the time, they're not. And so you have to know a little bit about the bearing or just make some assumptions. The safest assumptions, the best design, the sort of best practice, is to assume that you're only going to have forces F, Z, and Fx. And if it doesn't work out, if the structure is not stable or whatever it is you're trying to support is not stable, then change the design so that it is, rather than relying on a bearing like this to support a moment in either the X or the Z direction as shown there. So there's a little bit of nuance with this. You really have to know what you're doing with it, and you'll get used to it. It's not too bad. The hinge, you'll notice, has almost all of the supports. It's almost like a fixed connection between two parts. The only kind of load that it does not transmit is a moment about the y-axis. Of course, the reason for that is that a hinge is designed to pivot on the y-axis. You don't want it to resist a moment on the y-axis. You want the hinge to be able to open and close without resistance. So generally, if the support prevents translation, then there must be some type of force reaction. On the other hand, if rotation is what's prevented, then there must be some type of moment or force couple that's applied to resist that rotation. Some important notes. A single bearing can be used to prevent rotation. Now, I don't mean rotation about the axis of the shaft passing through it, but rotation in the other two directions. It's usually preferred, though, to use a pair of hinges or some other way of supporting the shaft going through the bearing so that the bearings don't have to take a moment load. Generally, what you want is only force reactions in your bearings. Sometimes you can't get by with that, but you'll see when I work some example problems how all of this works together. The equations of equilibrium. What equations do we have available to us? Well, here's where we have our full complement of equations. We've got all six. 3 force equations in the x, y, and z direction, and 3 moment equations in the x, y, and z directions, because now we're in 3D, so we get to use all of the equations, unlike 2D. We can write these as scalar equations of equilibrium by breaking up the vector force equation into components, where we say the sum of forces in the x equals the sum of forces in y equals the sum of forces in z, because they all have to be 0 to satisfy static equilibrium. And thus, that's why these things are called the equations of equilibrium. And then some of the moments in the x, y, and z are also exactly 0. If any of these equations were not true, then the free body that you're analyzing would accelerate. One thing to note about these moment equations, you can sum moments about any point you like. It doesn't even have to be a point on the body. If it makes your life easier, then it's a good point to sum moments about. If there are any forces that pass through the point that you choose to sum moments about, those forces have a 0 moment arm, and so they do not appear in the equation for the sum of moments. Now, it is entirely possible for a structure or a free body to be over-constrained. And in that case, you won't know how to solve such a free body because you don't have the knowledge from this class to solve it. When you go to Strength of Materials, you'll gain that knowledge. But for now, I'm not going to give you a problem that is statically indeterminate unless I want you to simply write, look, this can't be solved with statics. It is statically indeterminate. So what will happen is you'll have redundant constraints. And the way you'll notice that, you may not notice it right away until you get some practice, but the way you can notice it is once you set up all of your equations, you will find that you have too many unknowns and not enough equations. In other words, you will have more than 6 unknown forces and moments. And you won't be able to solve for them because you don't have enough equations. Now, like I said, when we get to Strength of Materials, you'll learn about deflection, and you'll learn how we can include sort of a spring equation or a deflection equation, taking each of the members of the structure or the free body to be to act like as if they act like springs, which they do really. So watch out for redundant constraints and problems that are statically indeterminate. All that means is statics can't determine an answer for you for that particular problem. Now here's a good practical question for you. Are statically indeterminate structures used in practice? Are they something that are worthwhile, or is it always, say, a mistake that some dumb engineer somewhere made by making their structure statically indeterminate? Actually, statically indeterminate structures are extremely common. There are many reasons for that. One is having a backup support, but we'll learn more about those in Strength of Materials. It's also possible for there to be an improper set of constraints that don't actually manage to completely constrain the free body. For example, if you have an L-shaped bracket like this, or rod, and it's connected to A and B with ball and socket joints, notice that a force P would tend to cause rotation about the line from A to B, because there's nothing to prevent that external load P from causing a moment arm about the AB axis. So while we have 6 unknowns, 6 equations, this is not a statics problem because it's not properly constrained. It will not stay still, it will simply move. Or I shouldn't say it will just move, it will accelerate, it'll change its speed. Here's another example where there are, apparently enough equations for the unknowns, but this beam on the lower left is not properly supported. Notice that there's a roller bearing at B that allows that end of the beam to simply pivot down about A. And so the force P is certainly going to cause a pivoting motion about A, simply because FB cannot resist it. It can't constrain it. It would be much better to put that rolling support below or above the I-beam. Of course, if it's above in the real world, you have to have some way of preventing the beam from moving away. You got to pull up on the beam. And so conceptually, it's better to think of it as just the roller being beneath the beam. But it's possible that a body could be unstable for some loading cases. So you've got to watch out for that. I had an example sort of like this. I'll try to describe it. I built a treehouse for my daughter many years ago. And I wanted it way up in the air so that I could mow underneath it. So it's fairly high as tree houses go. And I was putting it on a single tree. There was not 2 trees that I could use to make it nice and stable. I had to attach it to one tree. So I basically built it around the tree, sort of like a deck or something. But what I did is I put out at the four corners, I attached rods, and then I put those rods to either side of the tree. And in thinking about it, I realized, well, it could be unstable because since the rods are below, it's possible the whole deck could just pivot about this line that I had made, much like the first example in this slide. And so what I decided to do was to actually run a horizontal support that was tied to the tree that supported the center of the tree house and prevented the tree house from pivoting about its supports at the bottom. It was interesting, though, because there was still a problem. Because of the relatively low stiffness of the supports, when you get up in the treehouse, the whole treehouse would rotate around. You could run and stop all of a sudden. It would very uncomfortably just sort of rotate about the tree for what felt like an excessive amount of deflection. My solution to that was to add another bracket on the other side of the tree, and that took care of it. And of course, now I'm actually working on the tree house because the tree started growing around the supports that I built, and I even built my own tree house attachment bolts. You should look up tab bolts if you're interested in tree houses. But anyway, I literally just a week or so ago had to remove the nuts and cut the tree away a little bit and pull the supports out and then readjust them, put the nuts back on. And if the tree grows around it now, I'm going to be a grandpa with grandkids, and it won't matter at that point anyway. It'll be safe, and the supports will be grown into the tree. But anyway, it should last a lot longer now. But you really have to think about, especially when you're designing something, am I providing adequate constraint to resist whatever loads that there could be? Now, the only types of loads that can be applied are force in three directions and a moment in three directions. Had I considered that, I might have realized that a horizontal movement would allow the treehouse to rock back and forth, which was uncomfortable, but also a vertical moment would cause the treehouse to rotate about the axis of the tree, which was uncomfortable and not a proper constraint. So I guess the moral of the story is plan your tree houses better than I did.